We're now moving on to the second part of the review lesson for Chapter 7. To get started, we have a problem involving cell phones and two different schools. So in a small town with two schools, 1,000 students were asked if they had a cell phone. The results of the survey are shown below. So for School A, we have 365 students who have a cell phone, and we have 156 students who don't have a cell phone. And from School A, we surveyed about 521 students. And from School B, we had 408 students who had a cell phone, and 71 students did not have a cell phone, for a total of 479 students who were surveyed from School B. And the total number of students that were surveyed from School A and School B were 1,000 students. Okay, so the probability that a randomly selected student has a cell phone and is from School B to the nearest 100th. Okay, so we want to find the probability that a randomly selected student has a cell phone. So we surveyed 1,000 students, and the student must be from School B who has a cell phone. So School B has 408 students who have a cell phone. So that probability is simply going to be 408 divided by 1,000, which is going to be 0.41%, and that's going to be option B. Alright, moving on to the next problem. The data is the same, just the question will be different. This time I want the probability that a randomly selected student has a cell phone given that the student attends School B. Alright, so this is a conditional probability question along with Bayes' theorem. So basically I want to calculate the probability of having a cell phone given that they're from School B, and that's going to be simply the probability of having a cell phone and being from School B divided by the probability of coming from School B. Okay, so the probability of having a cell phone and coming from School B, well, that's going to be a total of 408. And the probability of coming from School B, well, that's going to be 479. So sorry, 479 doesn't represent the probability of B, it just represents the number of students that are from B. So when you divide 408 divided by 479, that will give you a probability of 0.85177. So that's going to be option number D. Alright, let's move on to the next review problem. Alright, in a particular city, 82% of the residents have a desktop computer, 47% have a desktop computer and a laptop computer, and 3% have neither a desktop nor a laptop computer. Okay, so the probability that a randomly selected home has a laptop computer is, alright, so this looks like a Venn diagram question. So let's draw a Venn diagram with two circles. And this middle region, the shared region, that's simply going to be 47% because that represents desktops and laptop computers. So blue will represent desktop, and this red color will represent laptop, and then we have 47% in the middle there. And then we can easily find the percentage for desktops only. This 35% comes from the 82 minus the 47, which should give you 35%. And this 3% have neither a desktop nor a laptop computer. Well, that's just going to be on the outside region, 3%. Now the question is the probability that a randomly selected home has a laptop computer is. Okay, so we've got to be very careful here. We're looking for the probability of having a laptop, and the laptop represents this entire circle here. Alright, it's not just this red region here, but we also have to include the area that's part of the blue region as well. So this whole region right here, this whole circle, that will represent laptops. So we need to find the probability in this region here. Alright, so let's get started with this. So if I put the letter Z here, we're essentially looking for what is Z plus 47%. And that will represent the entire red circle. So I know that Z plus 47%, which is the red circle, that must equal to 100% minus the 35% minus the 3%. Alright, so hopefully that makes sense, because the whole diagram has to equal to 100%. And if I minus the 35 and the 3, then I'm just left with the red circle here, which is 47 plus z. So z plus 47 will be 62%. So this 62% represents the entire red circle here. Alright, so the answer here will be B, 62%. And z here, you know, if 47 plus z equals to 62%, then the z will be 15%, which will be useful for the next problem. Alright, so for the next problem, we have the same data, but the question is different. Given that a randomly selected home has a desktop computer, the probability this home does not have a laptop computer is. Alright, so the word given is given in the question, so given that, so this is a conditional probability question. So let's set up our diagram once again. 47%, 35%, 3%, and this part right here will be 15%. So I want to find the probability that I don't have a laptop, given that I have a desktop. Right, so given that a randomly selected home has a desktop computer, which is this D right here, the probability this home does not have a laptop, and that's the L with the hat on. And sorry, there is a small little mistake here. It says C with a hat on. This should be L with a hat on. So the probability of not having a laptop computer, given that you have a desktop computer, is the probability of L hat and D divided by probability of D. Alright, so this numerator right here, that's simply going to be 35%. And that 35% is essentially this blue region right here. And basically this 35%, the reason why it's 35% is because this L with the hat means we're not in the laptop region. So the laptop region is right here, the red circle, 47 plus 15%. So L hat, which is this guy right here, that must represent the blue region, which is 35%. So that's how we get 35% on the numerator. And you know, not L hat plus D, so you know, D and L hat. Yeah, hopefully that's clear that this represents L hat and D. And the denominator here, the probability of just being a desktop, well, that's going to be this whole blue circle, which is going to be the 35% plus the 47%. So that's how you get the denominator there. And then you'll get 0.4268 as your final answer, and that's going to be option number B. Alright, let's move on. Alright, next question. Bag A contains 4 metal balls, which is the darker ones. So 1, 2, 3, and 4. And 6 glass balls. This is represented by the lighter color, so the 6 in this little region here. So bag A has a total of 10 balls, 4 metal and 6 glass balls. Bag B contains 5 metal balls and 2 glass balls. So for bag B, the 5 metal balls are here, 1, 2, 3, 4, 5, and the 2 glass balls are right here, 1 and 2. So we have a total of 7 balls in bag B. Okay, so in a game, a person rolls a die to determine which bag to pull a ball out of. If the die rolls a 1 or a 2, the ball is pulled from bag A. If the die comes up 3, 4, 5, or 6, then the ball is pulled from bag B. The probability of selecting a metal ball is. Alright, so we gotta draw a tree diagram here. So we got bag A and bag B. And the probability of selecting bag A is 1/3, because if you roll a die, the dice has 6 sides, and if it lands 1 or 2, which is 2 outcomes out of the 6, 2 divided by 6 is 1/3. And for bag B, the probability of selecting bag B is 2/3, and this 2/3, you get that from the numbers here, 3, 4, 5, 6. Those are 4 outcomes. and you have a total of 6 outcomes on the dice, so 4 divided by 6 is going to be 2/3. Now if you select bag A, then from bag A you can be metal or a glass ball. So for metal, that's going to be 40%, because you have 4 metal balls and you have a total of 10 balls in the bag, so 4 divided by 10 is 40%. And the glass situation, the glass balls will be 6 out of 10, which will be 60%. And for bag B, you also have metal and glass. And for bag B, you have 5 out of 7 metal balls, and you have 2 out of 7 glass balls. Alright, so the question is, the probability of selecting a metal ball is, well, that's simply going to be this branch right here, added on to bag B and the metal situation here. So this branch and bag A and metal as well. So that's going to be 1/3 times 4 divided by 10, which is 40%, plus the situation from bag B, which will be 2/3 times 5/7. You add these two situations together, and you will get a total of 128 divided by 210, and that's going to be 64 divided by 105, which will be option number C. Alright, let's move on to the next problem. Before we kind of move on to the next problem, we should we'll come back to this problem in order to help us with the next problem. But I believe some of the data from this problem will be useful for the next problem. Alright, so here's the next problem. Same data, but the question is, if a metal ball is selected, the probability it was pulled from bag B is. Okay, so basically I'm looking for the probability from bag B given that it's metal. So if a metal ball is selected, that represents this situation right here. It's a conditional probability. Then we want to know the probability that it was pulled from bag B, which is right there. And this is simply going to be the probability of bag B and metal divided by the probability of being metal. And in order to solve this kind of question, we need the data from the previous problem. And this is simply going to be 10 divided by 21 divided by 64 divided by 105. So let's just go back to the previous problem in order to get the data here. 10 over 21 and 64 divided by 105. Actually, this 64 divided by 105, this was the answer from the previous problem. And this 10 divided by 21 comes from the tree diagram. So let me just go back to the tree diagram here, and so basically here it is. Bag B and metal is 10 divided by 21. So in order to get this 10 divided by 21, we're simply taking this, we're basically calculating this situation right here, this 2/3 times 5/7, which is this branch right here. Bag B is 2/3, and the probability of being, a metal would be 5/7. So 2/3 times 5/7 is going to give you this 10 divided by 21. So this branch right here, bag B and metal, 2/3 times 5/7, that gives you 10 divided by 21. Alright, so once you divide these two fractions, you're going to get a total of 0.7812%, which is going to be option number D. Alright, let's move on to the next problem. Alright, for the next problem, similar situation, same bag A and bag B. This time, if two balls are pulled out of bag B without replacement, the probability they are both made of the same material is. Okay, so we got to draw another tree diagram here. Okay, so we have metal and glass. Okay, so if we're going from bag B, the number of metal balls is 5/7. So we have 5 metal balls, and we have a total of 7 balls in total, so 5/7. And the glass balls will be 2 divided by 7, because we only have 2 balls that are glass in bag B, 1 and 2. Now, if we go back, remember it says if 2 balls are pulled out of bag B without replacement. So if we go back to bag B And if we want to take out another ball from bag B, this time the number of metal balls will be 4 out of 6, and the number of glass balls will be 2 out of 6. And basically, if we take one ball from bag B and we remove it, we go from 7 to 6. And if that ball that we removed was a metal ball, then we go from 5 metal balls down to 4 metal balls. But the number of glass balls will be the same. It's 2 because we did not remove. In this situation here, we're removing a metal ball, not a glass ball, so we still have 2 glass balls left, but we only have 6 balls left in total for bag B. Now, if I pick out a glass ball first, then if I go into the bag again the second time, then I can have a metal ball or a glass ball. The total number of balls goes down from 7 to 6. I'll have 5 metal balls this time because I did not remove a metal ball when I take this situation here, the glass situation. But if I did remove a glass ball, then now I only have 1 glass ball, but now I have 6 total balls left in the bag. So I want to find the probability now that I want to find the situation where they are both made of the same material. So I want to find the probability of the same material, and that's simply going to be the metal and the metal added on to the glass and the glass. So this 5 over 7 is right here, this 4 over 6 is right there, so this is the probability of both balls being metal, and plus 2 over 7 times 1 over 6, that's the probability of both balls being glass, which is this branch right here. You multiply those together and add that to the branch over here, the 2 metal cases, and you'll get a total of 11 divided by 21, which is option A. Alright, next problem. A survey determines that in a particular town, 33% of the residents jog, 42% bike, and 12 do both activities. The probability that a randomly selected person does neither activity is. Okay, so we've got to set up a Venn diagram here with 2 circles. So blue and red. Blue will represent jogging and red will represent biking. 12% do both. Then if we know that, then 21% will jog only, and this 21% is found by taking 33 minus 12, and that means 30% bike only, and I get this 30% by going from 42 and subtracting 12. So 42 subtract 12 will be 30, and that will mean the probability of neither, which is the outside region, that's simply going to be 100 minus 21 minus the 12 minus the 30%, which will give you a total of 1 minus 63, 100 minus 63, and that's going to be 37%, which is option B. Alright, let's move on. Alright, so the probability of having a particular disease is 5%. The test to determine if a person has this disease is 83% accurate. The probability that a randomly selected person tests positive is. Alright, so we got to draw a tree diagram here. So we could have the disease or we could not have the disease. So there's a 5% chance of having the disease, and that means there should be a 95% chance of not having the disease. Now, if you have the disease, it could be accurate or not accurate. So if you have the disease, there's a 83% chance that you are indeed positive, and there will be a 17% chance that you're negative. So once again, you have a 5% chance that you actually have the disease, and then in order to make sure that you actually have the disease, you have to test if it's accurate or not. So if you have the disease and if you're positive, that's going to be 83%. And if you don't have if you have the disease and if it's negative, then it's 17%. And this negative just means that that's not accurate. So even though you do have the disease, there's a 17% chance that it's not accurate, so you may not have it. So hopefully this side of the branch, is straightforward here. But the next side of the branch might be a little bit confusing, because if you don't have the disease, you have a 95% chance that you don't have the disease. So then you need to see whether it's accurate or not. And if you don't have the disease, you want to be on negative, meaning that you really don't have the disease. And this branch right here, this will be the 83%. Okay, so over on the other side, the positive side, that meant you had 83%. So what this means is if you have the disease, then there's an 83% chance that it's accurate. Now over on this side of the tree, if you don't have the disease, which is 95%, then there's an 83% chance that you really don't have the disease. So the 83% would be over on this side in this case. And this 17% chance means that you may actually do have the disease, even though that you were tested that you don't have the disease. Alright, so hopefully that's okay. The probability that a randomly selected person tests positive is, okay, so for testing positive, that's going to be the probability of having the disease and being positive. So this situation down here, this branch, added on to the situation where you don't have the disease and it's positive on this side. So that's going to be 0.05 times 83% plus 0.95 times 0.17, which is going to be 0.203, and that's going to be option number A. Okay, so for the only tricky part about this problem is, I believe, just constructing the right-hand side of the tree diagram. Remember, if you don't have the disease, then there's an 83% chance that is actually right. You don't have it. You do test negative. All right, let's get on to the final problem in the review session. If 3% of the population has a specific disease, and the test for this disease is 92% accurate, the probability a person does not have the disease, given that the test result is positive, is. Alright, so for this problem, we need to draw another tree diagram. So you have the disease or you don't have the disease. So if 3% of the population has a specific disease, this will be 3%, and this will be 97%. And then once again, the test for this disease is 92% accurate. So if you do have the disease, there's a 92% chance that it is accurate, and there's an 8% chance that's not accurate. Now for the right-hand side of the tree diagram, if you don't have the disease, then there's a 92% chance that it's accurate. So if you don't have the disease, then there's a 92% chance that you will test negative, meaning you don't have the disease. And there's a 8% chance that it will be positive, meaning that you might have the disease. Alright, so now that we have the tree diagram set up, the question is the probability a person does not have the disease given that the test result is positive. Okay, so basically we're finding the probability of not having the disease given that we're positive, and this is simply going to be the probability of not having the disease and being positive divided by being positive. So this is going to be 97% times 8%. So that's simply this branch right here, 97 times 0.08. So this is basically not having the disease and being positive, which is the numerator right here. And then the bottom part, being positive, that's simply going to be the branches, this branch right here, we're going to have this 0.03 times 92%. This part right here is represented by this side of the branch, the right-hand side of the branch. And this part, the 97 times 0.08%, that's simply going to be this side of the branch right here, here, and here. And because we want to get the situations where we're positive here, and that represents the denominator for your calculator, and you get 0.73764, and that's going to be option number A. Alright, so that concludes the review session, and we'll see you again next time.